Stephen Hawking predicted that black holes aren't entirely black. They emit radiation, which is now named after him. This means that black holes slowly evaporate over trillions of years until they completely vanish. But what happens then? What happened before the Big Bang? And can we ever observe these relics of the Big Bang? Join us today as we answer these questions and more. Most astrophysicists are in agreement that black holes do indeed emit radiation. This isn't just because Stephen Hawking said so. There's a lot of evidence for it, including the fact that this radiation has been indirectly observed several times. We haven't seen it coming from our supermassive black hole at the center of our galaxy, but we have seen it coming from neutron stars. The reason black holes emit radiation is probably something you've experienced yourself. Ever put your hand near a fire and felt its heat even though there was nothing directly touching your hand? That's because energy can be transferred through radiation like light waves and heat waves. Similarly, the intense gravity around a black hole causes a sort of turbulence, creating ripples in space-time itself. These ripples are emitted as a form of radiation, but it doesn't come in the form we can see, hear, or feel. It comes in the form of particles called photons. The radiation that fills the region surrounding a black hole is called the photon sphere. Now, it's important to remember that while photons can carry energy, they don't actually have mass. So how does this work? Well, remember that photons travel at the speed of light, and Einstein showed that mass can be converted into energy. The faster an object moves, the more energy it has. So, if a photon is moving at the speed of light, then it must have some mass. And that's why the photon sphere of a black hole is both empty and incredibly energetic. Because the photons move at the speed of light, they never touch each other and they never slow down. The energy of the photons depends on their frequency. Visible light has frequencies between 430 and 750 terahertz, whereas the photons in the photon sphere of a black hole have frequencies lower than 1 hertz. Some of those photons will have frequencies higher than 10 to the power of 63 hertz. And if you were to convert those frequencies into equivalent masses, they would total up to about 10 to the power of 29 kilograms. That's the same as about 30 billion Boeing 747s. However, because the photons never slow down, they remain massless and invisible. But here's where things get weird. If the photons never slow down, then they never interact with each other. And if they never interact with each other, then they should never escape. So why do we see radiation escaping from the event horizon? This is because of the uncertainty principle, which states that no amount of measurement can ever be perfectly accurate. It also states that uncertainty is unavoidable, and that means that some photons can occasionally borrow a tiny bit of mass in order to escape. When they do this, they appear as particle-antiparticle pairs. One escapes and the other stays bound to the black hole, but it's only a temporary reprieve. Eventually, the photon that escaped will find another particle to borrow mass from, and it will fall back into the black hole along with its new partner, which will then create two new photons, one of which will escape and the other of which will stay trapped. This is basically the opposite of what normally happens inside a black hole. Instead of particles falling in and being crushed together, it's photons tunneling out and creating new particles. Okay, so that brings us back to the question, can black holes evaporate? Well, yes, they can. As photons escape from the surface of a black hole, they carry some of its mass away with them. But small black holes evaporate much faster than large ones. In fact, the rate of evaporation is inversely proportional to the mass of the black hole. Let's say you have a large black hole with a mass of 100 billion tons. It will evaporate once every 10 to the power of 68 years. But if you take a black hole with a mass of only 100 grams, it will only survive for 10 to the power of 36 years. Unfortunately for astronomers, black holes evaporate so slowly that it's almost impossible to detect unless they're fairly small. That's why researchers at Columbia University recently proposed building a constellation of satellites to look for Hawking radiation coming from primordial black holes. The idea is that a network of satellites could sweep a large enough area of sky to spot the telltale glow from evaporating mini black holes. But how big would these black holes have to be to actually see them? To answer that, let's look at the most common type of black hole that astrophysicists think might exist, the primordial black hole. Primordial black holes are black holes that formed in the early stages of the universe when it was a hot, dense quark gluon plasma. Now, I know what you're thinking. Isn't everything made of atoms and protons and neutrons and quarks? Aren't those fundamental? Well, yes, they are now, but that wasn't always the case. After the Big Bang, all matter was in a soup-like state. The early universe was so hot that particles like protons and neutrons couldn't hold together. As the universe expanded and cooled, the particles started to condense into larger and larger groups until eventually atoms formed. We call this period of rapid change the inflationary epoch because it is thought to have taken place during a period of exponential expansion in the early universe. What makes primordial black holes interesting is that they could have formed during this inflationary epoch. And because they formed in such large numbers, they could have produced the majority of dark matter in the universe. For a black hole to make up a significant portion of dark matter, it needs to have a mass between 1 and 100 billion tons. Now, the good news is that a black hole of that size would evaporate pretty quickly. The bad news is that it would evaporate in less than a second, but there's another possibility. Before a black hole evaporates completely, it can reach a state called the Planck star. A Planck star is the smallest possible black hole. Its radius is called the Planck length, and it is equal to about 1.6 by 10 to the power of negative 35 meters. The reason black holes can't get any smaller than this is because of the uncertainty principle. Gravity gets stronger the closer you get to a black hole. So if you squeezed a black hole, making it smaller, its gravity would get stronger. At a certain point, the gravity would become so strong that it would tear apart the very fabric of spacetime, causing the collapse of the black hole. If this happens, all the matter in the black hole is released at once, giving it a huge burst of energy. It's thought that this energy could leave behind a quantum remnant, kind of like a relic of the Big Bang. The energy released from a collapsing Planck star would be so high that it could create a baby universe. This means that primordial black holes could be one of the best ways to test the theory of eternal inflation, which says that our universe is just one of many universes that are constantly being created. In fact, there's a good chance that we already live in a bubble of eternal inflation. But that's a topic for another video. So what would we actually see if we could detect Hawking radiation? Well, it all depends on the size of the black hole. If it's big enough, we would see a bright flash of light similar to a gamma ray burst. If it's smaller, we would see X-rays, and if it's really small, we would see ultraviolet light. If we could see the radiation coming from primordial black holes, it would be like looking back in time to the very beginning of the universe. We could see what existed before the formation of atoms and before the formation of stars and galaxies. It would be a window into the past that would allow us to test some of the most fundamental theories in physics. At the moment, there's no direct detection of Hawking radiation, but that doesn't mean it doesn't exist. It may be that the key to detecting it lies in observing gravitational waves. Gravitational waves are ripples in space-time that travel at the speed of light. When two massive objects orbit each other, they cause ripples in space-time that radiate outward. In 2015, LIGO detected the first gravitational wave signal, which came from two black holes that merged. But this wasn't Hawking radiation. It was the signal from the merger of two black holes. What LIGO and other observatories need to do is detect the signal from a single black hole as it evaporates. That would be the true signal of Hawking radiation. In 2022, researchers used data from the Laser Interferometer Space Antenna to search for gravitational waves coming from the evaporation of a black hole. While they didn't find anything, they did set a limit on the strength of Hawking radiation. The problem is that even if we detect Hawking radiation, it won't necessarily mean that we understand quantum gravity. There are some theories that predict that Hawking radiation should come in the form of particles instead of gravitational waves. And if we detect those particles, then it would be evidence in favor of string theory or loop quantum gravity. But if we only detect gravitational waves, then it would suggest that the correct theory is something else, such as causal set theory or asymptotic safety. We're living in an exciting time for cosmology. The James Webb Space Telescope is helping us look further back in time than ever before. At the same time, experiments like LIGO are helping us probe the deepest mysteries of quantum gravity. Who knows what we'll discover next? Maybe we'll find evidence of other universes, or maybe we'll find the key to time travel. One thing is for sure, though, the future of cosmology is full of promise. So, do you want to learn more about the amazing discoveries being made in cosmology and astrophysics today? Do you want to learn about the latest research and discoveries without having to sift through the technical jargon? Then subscribe and join our community of over 1 million learners today.